There is a kind of sentence that sounds exaggerated until physics earns it. This is one of those sentences. What physicists have discovered about reality changes everything. Not because one experiment shattered the universe overnight. Not because a secret paper proved we live in a simulation. Not because some lab finally found the code of God hidden inside a particle detector. The change is slower than that. More serious than that. And in some ways far more disturbing. Because what has changed is not just one theory. It is the picture. The picture most people still carry in their heads. A world made of solid things. Objects sitting in empty space. Time flowing the same for everyone. Particles behaving like tiny pebbles. Observation meaning simply looking. The vacuum meaning nothing. Distance meaning separation. The present meaning a single universal now. That picture still feels natural. It also appears to be wrong in nearly every deep way that matters. The table in front of you does not feel solid because matter is little chunks packed tightly together like microscopic bricks. It feels solid because quantum fields refuse to let certain patterns overlap in certain ways. The empty space around you is not truly empty. Time is not universal. Particles are not small billiard balls in the classical sense. Measurement is not just passive witnessing. Black holes force physics to ask whether information can ever really disappear. Entanglement suggests the world is not cleanly made of independent little islands. And some of the most serious ideas in modern theoretical physics hint that space itself may not be fundamental at all. Think about that carefully. Not that space is curved. We already learned to live with that. Not that matter is made of atoms. That shock is old. But that the stage itself may not be primary. That what we call reality may be less like furniture arranged inside a room and more like a web of relations from which the room emerges only afterward. This is not mystical language. It is the pressure created when quantum theory, relativity, information theory, black hole physics, and high-energy theory all begin to lean in the same conceptual direction. The universe is not becoming less real. It is becoming less intuitive. The old world of things is giving way to a world of patterns. The old world of objects is giving way to a world of structure. The old world of passive observation is giving way to a world where what can be known depends on how physical systems become correlated. And if that sounds abstract, stay with it. Because the terrifying part is not that reality has become mathematical. The terrifying part is that it may never have been the kind of thing human common sense was built to understand. What if solidity is a negotiated effect? What if emptiness is crowded with latent activity? What if here and there are not as absolute as they feel? What if now is provincial? What if matter is not made of little pieces, but of stable excitations in something deeper? What if space itself is the byproduct of a more primitive order? And what if physics, after centuries of making the universe feel more measurable, has finally led us to a place where reality is not smaller, safer, or more familiar, but stranger, more relational, less object-like, and less centered on us than ever before? Tonight, we are going to follow that shift all the way down. Not into science fiction. Into physics. Into the decades-long convergence that has quietly replaced the human picture of reality with something colder, cleaner, and much harder to emotionally survive. Because what physicists have discovered does not merely change how the universe works. It changes what kind of thing the universe is. And once you see that clearly, it becomes difficult to go back to the old world. The world of solid things in empty space. That world was never waiting for us. It was only what reality looked like from far away. Before we go any further, we need to be honest about the title. Physicists did not wake up one morning, find a single impossible signal, and declare reality rewritten by lunchtime. The discovery here is not a headline-sized event. It is a convergence. A long, disciplined accumulation of results across quantum mechanics, relativity, field theory, thermodynamics, particle physics, information theory, and cosmology that, taken together, point toward a profoundly different image of the real. The key phrase is taken together. Because each revolution, on its own, can be misunderstood. Quantum mechanics can be isolated as, tiny particles are weird. Relativity can be reduced to, time slows down when things move fast. Field theory can be taught as just a technical replacement for particles. Black hole physics can be packaged as a niche problem for specialists. Information theory can sound like engineering. Symmetry can seem like pure mathematics with no emotional content. But when these are layered on top of one another, something larger appears. The universe stops looking like a warehouse of objects. It starts looking like a structured negotiation. What exists is not merely what sits there. What exists, at the deepest level we know how to describe, is bound up with fields, constraints, transformations, correlations, conservation laws, measurement structure, and geometry. The old intuition says reality is made of things. Physics increasingly suggests that reality may be made of relations that can stabilize into thing-like behavior. That is a very different claim. And it does not mean chairs are illusions or planets are fake or nothing is real. It means that what feels fundamental to us may be emergent. That what feels primary may be derivative. That solidity, locality, separateness, and even the flow of time may be features of a certain level of description rather than the bottom floor of existence. In this documentary, we are going to move carefully. We will start with common sense, because common sense is the first thing reality betrays. Then we will move into why solid objects are not really solid in the classical sense, why modern physics talks in terms of fields rather than little pellets, why the vacuum is physically active, why relativity killed universal simultaneity, why quantum measurement is not simple looking, why entanglement makes separateness suspect, why information became a physical quantity with teeth, why black holes forced a crisis in reality's bookkeeping, why symmetry governs almost everything, why particles may be better understood as excitations than objects, why some physicists suspect spacetime itself is emergent, and what we still absolutely do not know. And through all of this, one distinction will matter constantly. Established results are not the same as frontier speculation. It is well established that matter is described extremely successfully by quantum field theory. The vacuum is not classical emptiness. Time is not absolute. Entanglement is real. Information has physical meaning. Black holes make deep demands on consistency. Symmetry is foundational. It is much more speculative that spacetime literally emerges from entanglement in a complete final sense. Holography is the universal key to all reality. Information is the single deepest substance of existence. Space and time are fully non-fundamental in the ultimate theory. We will distinguish those carefully. But even staying strictly on established ground, the shift is already enormous. Because the modern physical picture has done something psychologically difficult. It has not removed mystery. It has moved mystery inward. The mystery is no longer only out there in distant galaxies or black holes. It is in the table. In the vacuum. In simultaneity. In what a particle is. In what a measurement is. In what it means for one event to be separate from another. Reality did not become simpler when physics matured. It became less obedient to human categories. And maybe that is the real discovery. Not that the universe is chaotic. But that it is precise in a language our instincts were never built to speak. So from this point on, we are not going to ask the childish version of the question. Not, what weird trick did physicists just find? But this. What picture of reality are physicists being forced toward by the combined weight of modern theory and experiment? And if that picture is right, even approximately right, what kind of universe have we actually been living in all along? There is a kind of sentence that sounds exaggerated until physics earns it. This is one of those sentences. What physicists have discovered about reality changes everything. Not because one experiment shattered the universe overnight. Not because a secret paper proved we live in a simulation. Not because some lab finally found the code of God hidden inside a particle detector. The change is slower than that. More serious than that. And in some ways far more disturbing. Because what has changed is not just one theory. It is the picture. The picture most people still carry in their heads. A world made of solid things. Objects sitting in empty space. Time flowing the same for everyone. Particles behaving like tiny pebbles. Observation meaning simply looking. The vacuum meaning nothing. Distance meaning separation. The present meaning a single universal now. That picture still feels natural. It also appears to be wrong in nearly every deep way that matters. The table in front of you does not feel solid because matter is little chunks packed tightly together like microscopic bricks. It feels solid because quantum fields refuse to let certain patterns overlap in certain ways. The empty space around you is not truly empty. Time is not universal. Particles are not small billiard balls in the classical sense. Measurement is not just passive witnessing. Black holes force physics to ask whether information can ever really disappear. Entanglement suggests the world is not cleanly made of independent little islands. And some of the most serious ideas in modern theoretical physics hint that space itself may not be fundamental at all. Think about that carefully. Not that space is curved. We already learned to live with that. Not that matter is made of atoms. That shock is old. But that the stage itself may not be primary. That what we call reality may be less like furniture arranged inside a room and more like a web of relations from which the room emerges only afterward. This is not mystical language. It is the pressure created when quantum theory, relativity, information theory, black hole physics, and high-energy theory all begin to lean in the same conceptual direction. The universe is not becoming less real. It is becoming less intuitive. The old world of things is giving way to a world of patterns. The old world of objects is giving way to a world of structure. The old world of passive observation is giving way to a world where what can be known depends on how physical systems become correlated. And if that sounds abstract, stay with it. Because the terrifying part is not that reality has become mathematical. The terrifying part is that it may never have been the kind of thing human common sense was built to understand. What if solidity is a negotiated effect? What if emptiness is crowded with latent activity? What if here and there are not as absolute as they feel? What if now is provincial? What if matter is not made of little pieces, but of stable excitations in something deeper? What if space itself is the byproduct of a more primitive order? And what if physics, after centuries of making the universe feel more measurable, has finally led us to a place where reality is not smaller, safer, or more familiar, but stranger, more relational, less object-like, and less centered on us than ever before? Tonight, we are going to follow that shift all the way down. Not into science fiction. Into physics. Into the decades-long convergence that has quietly replaced the human picture of reality with something colder, cleaner, and much harder to emotionally survive. Because what physicists have discovered does not merely change how the universe works. It changes what kind of thing the universe is. And once you see that clearly, it becomes difficult to go back to the old world. The world of solid things in empty space. That world was never waiting for us. It was only what reality looked like from far away. Put your hand on a table. It feels hard. Stable. Resistant. Certain. This sensation is one of the oldest pieces of evidence human beings ever trusted. The world pushes back. Therefore it is solid. But modern physics says something much stranger is happening. Atoms are mostly not solid little marbles pressed against one another. They are structured systems whose size is determined by quantum behavior. Their electrons do not orbit like planets in any classical sense. Their interactions are governed by electromagnetic fields and quantum states. And when one object seems to touch another, what you are really feeling is not tiny billiard balls colliding in the everyday sense. You are feeling force. More precisely, you are feeling the electromagnetic interaction between charged constituents. Along with quantum rules, especially the Pauli exclusion principle for fermions, preventing matter from collapsing into the same states. That table does not stop your hand because its atoms are miniature pebbles packed so tightly that no room remains. It stops your hand because the allowed quantum states of the electrons in your hand and the electrons in the table do not simply permit the same configurations, and because electromagnetic interactions grow violently repulsive at close approach. What you experience as contact is really a refusal. Matter says no. Not in language. In structure. This is a very different image from the one intuition gives you. The old image is that solids are solid because they are full. The better image is that solids are solid because the fields and quantum rules governing their constituents create stable patterns of resistance. So when you knock on wood, you are not encountering a featureless block of stuff. You are encountering the behavior of electrons, nuclei, fields, and statistical rules assembled into a macroscopic form. This is already enough to change how reality feels. But it gets stranger. If you zoom into an atom, almost all the volume is not occupied the way ordinary language imagines occupation. The nucleus is tiny compared with the atom's full size. The electron cloud is not a little set of classical pellets racing around fixed tracks. It is a quantum mechanical structure, described by wave functions and probabilities of measurement outcomes. In that sense, the solidity of matter is not the solidity of filled geometry. It is the solidity of stable exclusion and interaction. A pattern can be robust without being tiny bricks all the way down. That distinction is one of the quiet revolutions of modern physics. And it has consequences beyond touch. Why do atoms form the shapes they do? Why is chemistry possible? Why don't electrons all collapse into the lowest energy state around a nucleus in a way that erases structure? Why do white dwarfs resist collapse? Why do neutron stars exist? Why is there a periodic table instead of homogeneous featureless matter? Spin, statistics, exclusion, and interactions. Remove those, and the world does not just become different. It stops looking like a world at all. This is why it is misleading to think of physics as having explained matter by simply finding smaller pieces inside it. Physics also discovered that the behavior of those pieces is nothing like what common sense means by piece. And matter itself is not merely stuff. It is organization. A stable hierarchy of patterns sustained by law. You can already see the motif emerging. The real is not dissolving. It is becoming more conditional. More relational. More structured. What feels primitive, hardness, substance, contact, turns out to be emergent from interactions we do not directly perceive. And this means something emotionally difficult. The world closest to us is not the world most directly given by fundamental description. The world closest to us is the world after many layers of emergence have stabilized. Our experience begins late. By the time you feel a table, reality has already done a great amount of work. Quantum fields. Bound states. Electromagnetic interaction. Fermionic statistics. Decoherence. Thermal behavior. Material structure. Macroscopic rigidity. Touch is not a primitive window. It is the end result of an enormous physical story. Which raises a natural question. If matter is not, at bottom, made of little hard grains in empty space, then what does modern physics say is really there? The answer that currently works best is one of the strangest and most successful ideas in science. Not particles first. Fields first. A universe of fields, in which what we call particles may be localized excitations rather than tiny objects with independent little cores. And once that shift happens, the entire architecture of reality begins to feel different. If you were educated in the older intuitive style, you were probably taught that the universe is made of particles, electrons, photons, quarks, neutrinos, maybe a few force carriers added later. That is not wrong exactly. But it is incomplete in a way that becomes dangerous if you stop there. Because in the modern framework of quantum field theory, the fundamental description is not little things moving through space, in the classical sense. It is fields. Fields are not just visual aids. They are not secondary conveniences layered on top of more real particles. They are the central objects of the theory. At every point in space, or more carefully, in spacetime, quantum fields exist. The electron field, the photon field, quark fields, gluon fields, the Higgs field, and others depending on the theory. What we call a particle is, in this picture, a quantized excitation of a field. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. The world begins to look less like a box of tiny objects and more like an ocean of underlying entities whose ripples come in discrete units. This analogy to ripples is helpful, but only up to a point. Fields are not classical fluids. Still, the emotional correction matters. The particle is not necessarily the thing. The field is deeper. This changes how you imagine existence. Instead of empty space with bits of matter sprinkled through it, you get a universe in which the empty background is already full of field structure, and particles are events or excitations within that structure. The old picture. Objects inhabit space. The newer picture. Field structure pervades spacetime, and object-like behavior emerges in certain regimes. This is not philosophy imposed on physics after the fact. This is the language of the framework that predicts experiments to absurd precision. Quantum electrodynamics, built within this field language, is among the most accurate theories human beings have ever produced. Its predictions for quantities like the electron's magnetic moment agree with experiment to astonishing decimal places. So when physics talks this way, it is not trying to be poetic. It is trying to be correct. There is also something conceptually beautiful about fields. They unify. Instead of treating forces as mysterious actions across emptiness, fields let interaction be local. Charges influence the electromagnetic field, the field influences charges. Matter and radiation become part of a common formal structure. Gauge symmetries organize the interactions. Conservation laws arise from deep invariances. Reality begins to look lawful in a very severe way. Not as a collection of accidental little things, but as patterns permitted by underlying symmetries and field dynamics. And then the strangest question arrives. If fields are everywhere, what is nothing? What does it mean for space to be empty if the fields are still there? If particles are absent but the fields remain, have we actually reached nothing? Or have we only reached the lowest energy behavior of something deeper still? This is where the vacuum enters, and the vacuum is one of the places common sense suffers its most complete defeat. Because emptiness, in modern physics, is not simply absence. Emptiness has rules. Emptiness has energy structure. Emptiness can have measurable effects. Which means the old human contrast between something and nothing starts to break. And once that line breaks, reality becomes stranger in a way most people never fully recover from. If you remove the stars, the planets, the gas, the dust, the radiation, the molecules, the atoms, and all the obvious matter from a region of space, intuition says you are left with nothing. Physics says not so fast. Because what remains may still include fields in their lowest energy states. It may still include quantum fluctuations. It may still carry structure, boundary sensitivity, geometry dependence, and measurable effects. In modern theory, the vacuum is not classical emptiness. It is the vacuum state. That phrase is easy to underestimate. It sounds like a technicality. It is not. A vacuum state means the lowest energy state of a field-theoretic system relative to the description in use. No particles need be present in the ordinary detectable sense, but the fields are not gone. The stage is not absent. The degrees of freedom remain. This is one reason the word nothing becomes dangerous in physics. The vacuum is not a blank metaphysical void. It is a physical condition. And physical conditions can do things. The Casimir effect is one famous example. Place conducting plates very close together in vacuum, and they can experience a measurable force due to how allowed quantum modes differ between inside and outside regions. However one presents the interpretation carefully, the important lesson is clear: what looks empty is not physically inert in the classical sense. Vacuum structure also appears in spontaneous symmetry breaking and the Higgs mechanism. The Higgs field has a non-zero vacuum expectation value. In loose language, the field fills space in such a way that interacting particles acquire mass through their coupling to it. Even if the simplified popular versions are imperfect, the emotional point survives. Empty space is not a mere backdrop with zero character. It participates. Then there is quantum fluctuation language, which must also be handled responsibly. Popular science often says particles constantly pop in and out of nothing. That phrase is catchy and often misleading. But it points towards something real. Quantum fields in vacuum are not identical to classically frozen zero-activity emptiness. The vacuum has non-trivial structure in correlation, functions and observable consequences. And once gravity enters the story, the vacuum becomes even more unsettling. Acceleration can change what counts as vacuum for an observer. Curved spacetime can complicate particle definitions. Horizons can turn vacuum structure into perceived temperature, as in the Unruh effect. Conceptually and Hawking radiation in black hole settings. So the vacuum is not just space with no stuff. It is a physically meaningful state whose properties depend on theory, observer, geometry, and interaction. That sentence alone should be enough to make the old worldview unstable. Because if emptiness is not truly empty, then even absence has architecture. The universe is never a simple container. It is active at a level deeper than common sense ever prepared us for. There is also a philosophical bite here. For most of human history, nothing functioned as the mental opposite of being. Nothing was what remained when being was stripped away. Modern physics has not solved the metaphysical meaning of nothing. But it has certainly damaged the everyday one. It has shown that the absence of particles is not the absence of structure. That the lowest energy state is still a state. That emptiness can carry consequences. In other words, what feels like a void may be a disciplined form of hidden order. And this leads naturally to time. Because once you accept that matter is less solid than it seems and emptiness less empty than it seems, one more ordinary assumption comes under pressure. The assumption that time is a universal background flowing the same for everyone. Physics did not merely complicate time. It abolished the naive version. It told us that now is local, that clocks do not all agree, and that time can no longer be treated as The invisible river in which the world simply floats. The death of absolute time is one of the moments where reality stopped being emotionally familiar. And once that happened, the old picture of a single shared world became harder to maintain. Nothing in human experience feels more universal than time. Morning becomes afternoon. A child becomes an adult. A candle burns down. A heartbeat passes. A sentence ends. It is therefore deeply offensive, at first, that physics should interfere with time. And yet that is exactly what relativity did. Before Einstein, the dominant intuition, formalized in Newtonian mechanics, treated time as absolute. A universal ticking. A hidden cosmic clock. Different observers might disagree about where things were, but not about whether two distant events were truly simultaneous. Relativity destroys that comfort. Special relativity tells us that the speed of light is invariant for all inertial observers. To preserve this, measurements of space and time must adjust. Lengths contract. Time dilates. Most disturbingly for intuition, simultaneity becomes relative. Two events that look simultaneous in one frame need not be simultaneous in another moving frame. This is not optical illusion. Not delayed signal confusion. Not human error. It is structure. There is no universal, now, slicing across the cosmos in the way common sense imagines. Already that is enough to change everything. Because if now is not universal, then reality is not laid out as a single present shared identically by all observers. Different world lines cut spacetime differently. The universe becomes less like a frozen set of objects inside one common time, and more like an interconnected geometry of events, whose temporal ordering depends partly on relation. Relation again. This is the recurring wound common sense keeps suffering. Not object first. Relation first. General relativity goes further. Gravity is not merely a force pulling masses through space and time. Gravity is the geometry of spacetime itself. Matter and energy tell spacetime how to curve, curved spacetime tells matter how to move. Whether or not one likes this slogan, it captures something transformative. The stage is not fixed. The stage participates. Time slows near mass. Clocks tick differently depending on gravitational potential. Paths of light bend. Space and time are not passive containers. They are dynamical. Think about how radical that is. The old human picture imagined a universe of things moving around on a neutral background. Relativity says the background itself is physical. And once the background becomes physical, it can no longer be taken for granted. Time becomes geometry. Geometry becomes dynamics. Measurement becomes frame-dependent. The world stops being a single common-sense inventory and becomes a spacetime structure. This has practical consequences we already live with. GPS satellites require relativistic corrections. High-energy particles live longer when moving rapidly relative to us. Gravitational redshift is measured. Relativity is not philosophical decoration. But the emotional consequence is harder to absorb. There is no God's eye present readily available inside the theory. A universal now would have been psychologically reassuring. It would have made reality feel unified in the way our storytelling instincts prefer. Instead, physics gives us a world where, at the same time, is not absolute at cosmological scales. That does not mean all moments exist identically in every metaphysical interpretation. It does mean the ordinary intuitive present is not built into fundamental law the way we thought. So even time, the invisible thread we trust more than almost anything, turns out not to be what it seems. And when you combine that with quantum theory, the discomfort multiplies. Because it is one thing for time to be relative. It is another for observation itself to become problematic. Most people hear observer in quantum mechanics and imagine a person looking at a system. That is almost never the right way to think about it. What observation means in physics is more subtle, more physical, and more destabilizing than mere seeing. And once you understand that, reality stops looking like a stage populated by pre-written facts, waiting for human attention. It begins to look like a process in which what can be said depends on how systems become tied together. Quantum mechanics is often introduced with its most theatrical features: wave-particle duality, probabilities, uncertainty, measurement. The famous question of what happens before observation. Popular culture did what it always does: it turned this into magic. Consciousness creates reality. Nothing exists until you look. The universe needs a mind to become definite. These claims are seductive. They are also, in most versions, bad physics. Observation in quantum mechanics is not fundamentally about eyeballs. It is about physical interaction. It is about when a system becomes correlated with another system in such a way that certain outcomes become effectively registered, amplified, and classically available. The trouble is that the formalism does not map neatly onto classical everyday language. A quantum system can evolve according to the Schrödinger equation in superposition-like ways. Yet when measurements are made, we obtain definite outcomes. How exactly that transition is to be interpreted remains one of the deepest conceptual questions in physics. But the minimum lesson is already enough to trouble intuition. Observation is not passive witnessing of prepackaged reality. Observation is participation in a measurement structure. A detector is not a spectator. It is part of the event. An apparatus interacts, amplifies, decoheres, records. And the outcome we talk about as the result is not just reality politely waiting on a shelf. It is reality after a physical coupling has occurred between system, device, environment, and later observers. This is why quantum theory feels so unnerving. It does not simply say we are ignorant of hidden classical values in the everyday way. In its standard successful form, it says the very grammar of prediction is built around states, amplitudes, operators, and measurement outcomes that do not fit the old object-with properties model cleanly. Now, physics remains divided on interpretation. Copenhagen-style views, many worlds approaches, relational quantum mechanics, cubist ideas, objective collapse models, pilot wave theories, these differ in what they say the formalism means. Some are more conservative, some more radical, some more ontological, some more epistemic. We should be careful here. What is established is not a single philosophical interpretation. What is established is the extraordinary empirical success of quantum theory and the fact that classical naive realism about microscopic systems is no longer easy to maintain. That already changes everything. Because it means reality may not be composed of properties simply sitting there in the way common sense wants. What can be meaningfully said about a system is linked to measurement context and dynamical relation. Once again, relation. Once again, the object-centered picture weakens. There is also decoherence, one of the most important clarifying concepts in modern quantum foundations. Decoherence does not by itself solve every interpretive question. But it explains a great deal about why the macroscopic world appears classical. When a quantum system becomes entangled with a large environment, interference between certain alternatives becomes effectively inaccessible. Preferred stable states emerge in practice. The world starts looking definite not because quantum law stops, but because the information about relative phases becomes dispersed into the environment in ways that cannot realistically be reversed. The world classicalizes. Or seems to. This is not magic. It is not mind over matter. It is physical correlation structure spreading outward. And that is one reason the measurement problem is so rich. It lives at the boundary between what the theory predicts beautifully and how definite experience arises from it. The lesson for our documentary is this. Observation is not simple seeing because reality is not a museum of fixed microscopic facts waiting for a gaze. Reality is a network of evolving physical relations in which what becomes definite for us depends on the architecture of interaction. That phrase may be one of the deepest redefinitions physics has forced on us. Not seeing reveals the world. Structured interaction reveals the world. And once that is true, separateness itself becomes harder to trust. Because quantum mechanics has one more insult prepared for common sense. Entanglement. A phenomenon so repeatedly confirmed that it can no longer be treated as philosophical ornament. And so strange that Einstein himself regarded its implications with suspicion. Entanglement does not erase distance. But it does something arguably worse. It tells us that separate systems are not always fully describable as separate. And that means the world may be stitched together more deeply than locality-trained intuition ever expected. Imagine two systems interacting and then parting ways. Common sense says they separate. What happens to one is now its business. What happens to the other is its business. Distance restores independence. Quantum mechanics says not always. When systems become entangled, the state of the whole cannot, in general, be written as a simple product of independent states of the parts. The full description belongs to the composite system. Correlations appear that no classical local hidden variable account can fully reproduce if quantum predictions hold. An experiment has repeatedly sided with quantum theory. Bell's theorem sharpened the issue. Subsequent tests, increasingly sophisticated, ruled out broad classes of local hidden variable explanations. Nature does not behave as though the world is simply made of independently pre-equipped little pieces carrying complete local instructions. This does not mean signals travel faster than light in the ordinary communicative sense. Entanglement is not a telegraph. It does not let you send usable information instantaneously across space. But it does something conceptually almost as violent. It says that the state of reality may not factor into separately possessed classical properties of distant parts. The whole comes first. That sentence is easy to say and hard to emotionally survive. The whole comes first. At least in certain respects, the universe does not always permit the decomposition our instincts demand. Separate objects, yes. Separate laboratories, yes. Separate measurement outcomes, yes. But the underlying quantum description can preserve a unity not exhausted by spatial separation alone. This is why entanglement has become one of the philosophical fault lines of modern physics. Because it undermines the picture of a universe fundamentally made of local self-sufficient beads. Instead, it suggests reality contains relational structure that cannot always be reduced to independent local pieces. Again, relation. Again, the object picture weakens. And this is not just metaphysical drama. Entanglement is now central in quantum information science, quantum computing, quantum cryptography, condensed matter theory, black hole puzzles, and some of the most speculative ideas about spacetime emergence. A phenomenon once treated as a bizarre side effect has become one of the main roads into the future of physics. There is a poetic irony there. One of the things that most offended classical intuition may turn out to be one of the deepest clues about what reality is made of. Or at least how it is stitched. Still, we must stay disciplined. Entanglement does not mean everything is spiritually connected in a vague mystical sense. It does not abolish locality in every operational respect. It does not give you magical causation. But it does mean the world structure of correlation is richer than classical separateness allows. The universe is not just laid out as disconnected chunks plus forces between them. It contains composite states that make the whole primary in certain descriptions. That is a remarkable statement. And it leads naturally to information. Because once correlation becomes central, information stops sounding like a human concept. Layered onto nature and starts looking like something nature itself keeps account of. Information becomes physical. Not metaphorically. Not merely technologically. Physically. And when that happened, physics gained a new language for speaking about entropy, computation, measurement, black holes, and even the limits of what can happen in the universe. Reality ceased to be just matter and motion. It became, in part, a system of constraints on information. For a long time, information sounded secondary. Useful, yes. But secondary. After all, what is information supposed to be? Words? Messages? Bits on a hard drive? A human abstraction imposed on matter? Then 20th century physics started giving a harder answer. Information is not outside physics. It is inside it. Entropy already hinted at this through statistical mechanics, where macroscopic properties depended on vast numbers of microscopic configurations. Thermodynamics and probability began to blur. Then came Shannon's formal theory of information, which was not originally about atoms or cosmology, but gave science a rigorous language for uncertainty, compression, and communication. Sooner or later, the wall between information and physics had to break. And when it did, everything sharpened. Landauer's principle gave one famous slogan: information is physical. Erase a bit, and there is an energetic cost. Computation is not abstract angel work floating above matter. It must be embodied. Memory must live somewhere. Correlation must be stored somehow. Information processing is constrained by thermodynamics. This matters because it transforms information from a human bookkeeping convenience into a player in the deep architecture of law. Once information is physical, questions like these become urgent. Can information truly be destroyed? What is the relationship between entropy and knowledge? What does a measurement record cost? How much information can a physical region contain? What happens to information that falls into a black hole? Can spacetime geometry itself be tied to informational structure? These are no longer soft philosophical questions. They become hard physical ones. And something extraordinary happened once black holes entered the story. Black holes are not just collapsed stars. They are stress tests for consistency. When Bekenstein and Hawking connected black holes to entropy and temperature, the shock was enormous. A black hole has entropy proportional to the area of its horizon, not its volume. It radiates thermally in quantum field theory on curved spacetime. It can, in principle, evaporate. Immediately, the bookkeeping crisis begins. If a black hole forms from matter carrying detailed information and then evaporates into thermal radiation, what happens to that information? If it disappears, quantum theory seems to suffer a profound wound because unitary evolution is supposed to preserve information in the relevant sense. If it survives, how? Where? In what form? Encoded how in the outgoing radiation? This is not a niche detail. It is a collision between gravity, quantum mechanics, thermodynamics, and information. And once those domains collide, the old picture of reality as things in space evolving over time no longer feels remotely sufficient. Reality begins to look like a bookkeeping miracle. The universe keeps accounts. Charge, energy, momentum, angular momentum, and perhaps information in a deep, nearly sacred sense, sacred not as religion, but as consistency. This is why information became one of the conceptual currencies of modern fundamental physics. Not because everything is just information, in some simplistic sloganized way. That is too strong, too loose, too premature. But because information appears wherever physics tries to describe what can be distinguished. Preserved, lost, transmitted, encoded, hidden, or reconstructed. That means the universe is not merely made of stuff. It is governed by what can remain knowably related to what. And nowhere does that become more dramatic than in black holes, where reality seems to approach a contradiction unless some deeper rule saves it. Black holes are where physics stops being comfortable with its own categories. And that is why they have become one of the great laboratories for discovering what reality might really be. A black hole is one of the few places in physics where awe and crisis meet cleanly. It begins simply enough. Take enough mass energy, compress it beyond a critical threshold, and gravity becomes so intense that not even light can escape from within the event horizon. Already that is enough to disturb intuition. But black holes became truly revolutionary when quantum theory was brought into the picture. Jacob Bekenstein proposed that black holes should have entropy. Stephen Hawking showed that black holes radiate thermally when quantum field effects are considered near the horizon. That meant black holes are not perfectly black. They have temperature. They can lose mass. They can evaporate. Now the danger appears. If something falls into a black hole, the external world seems to lose access to the detailed information specifying that matter's precise quantum state. If the whole later evaporates into nearly thermal radiation with no such detail, then information appears lost. But standard quantum mechanics resists that conclusion violently. The evolution of a closed system is expected to be unitary. Information in the relevant quantum sense should not simply vanish. So which principle dies? Does quantum theory fail? Does black hole evaporation preserve hidden correlations? Does information stay on the horizon somehow? Does it leak out slowly? Is spacetime itself misleading us about inside and outside? Do new non-local structures appear? Does holography rescue consistency? These are not decorative questions. They are some of the deepest questions in modern theoretical physics. And the extraordinary thing is that black holes pushed physicists toward a picture where geometry, entropy, information, and quantum theory no longer look separate. The area law for black hole entropy suggested something radical. The number of degrees of freedom associated with a region might scale with boundary area rather than naive volume expectations. That is one root of the holographic idea. Not the pop culture version that says reality is fake. The more serious version that says the information content or full description of a gravitational region may have a dual relation to a lower dimensional non-gravitational theory on its boundary. This remains clearest in special theoretical settings, especially anti-de Sitter/conformal field theory. Correspondence. We must be careful here. Holography is immensely powerful and influential. But its exact universal meaning for our actual cosmological universe remains an area of active frontier work, not finished doctrine. Still, even the hint is enough to shake the old worldview. If the universe, or aspects of gravitational reality, can be encoded in ways that do not respect our naive object-in-volume intuitions, then the world may be even less like a classical container than we thought. Black holes therefore perform a brutal service. They take our concepts, space, time, inside, outside, entropy, information, locality, and force them into conflict until a deeper structure seems necessary. That is what a genuine scientific crisis looks like. Not chaos. Pressure. Pressure until a more coherent picture forms. The black hole information problem has generated decades of work. Complementarity. Holography. Firewall debates. Replica wormholes. Island formulas. And deeper reflection on what quantum gravity must preserve. We do not yet have unanimous closure on the deepest interpretive meaning. But one lesson already stands out. Reality is more conservative than common sense. It may protect its bookkeeping in ways that require us to sacrifice our naive geometry instead. That is a terrifying thought. It suggests that when forced to choose between space works like we think and the laws preserve consistency, nature may be willing to deform our intuitions about space, horizons, and locality before allowing the books to fail. The universe may not care if our picture survives. It seems to care that the accounting does. That idea prepares us for symmetry, because symmetry is the next place where reality reveals that what exists is tightly constrained not by taste or accident, but by deep formal invariances. And if black holes tell us the universe keeps severe accounts, symmetry tells us the universe was built according to a grammar more rigid than our sensory world reveals. Symmetry sounds decorative. A snowflake. A face. A pattern in a mosaic. In fundamental physics, symmetry is not decoration. It is law's architecture. A symmetry means that some transformation leaves the essential form of the laws unchanged. Shift in time. The laws look the same. Shift in space. The laws look the same. Rotate. The laws look the same. And Emmy Noether showed one of the most beautiful facts ever discovered. Continuous symmetries are tied to conservation laws. Time translation symmetry gives energy conservation. Spatial translation symmetry gives momentum conservation. Rotational symmetry gives angular momentum conservation. This is not a coincidence. It is a deep identity between invariance and bookkeeping. Already this should change how reality feels. The universe is not law-like because it happens to keep repeating habits. Its lawfulness is bound to symmetry structure. Then gauge symmetries take this further. Modern particle physics is built from gauge principles organizing the interactions of fields. Quantum electrodynamics, the weak interaction, and quantum chromodynamics are not just lists of forces. They arise from structured symmetry requirements. So when physicists ask why the world has the interactions it does, they are often really asking, what symmetry is being respected? What symmetry is being hidden? What symmetry is being broken? And symmetry breaking is where the world becomes especially rich. A system can obey underlying laws with a high symmetry while settling into a state that does not display that full symmetry openly. This happens in many domains. A perfectly upright pencil on its tip respects rotational possibilities, but once it falls it picks a direction. Cooling can produce ordered phases. Fields can settle into non-zero vacuum values. The Higgs mechanism lives in this family of ideas. Without going too far into oversimplified pop science shorthand, the point is that the vacuum itself can select a structure that distinguishes behaviors and gives particles effective mass through interaction. So the world we see is not merely the raw expression of fundamental possibility. It is a broken symmetry world. A selected world. A world whose visible features depend on how deeper laws settle into actual states. This should sound familiar now. The world of experience is downstream. Again and again, physics keeps telling us this. What you see is the cooled, stabilized, symmetry-broken face of something more austere. That is one reason matter looks like matter. That is one reason forces separate the way they do. That is one reason masses differ. That is one reason the universe is not a featureless blur of undifferentiated possibility. Difference emerges from structured breaking. The terrifying part is not that the universe is chaotic beneath appearances. It is that it is almost too elegant. Too constrained. Too grammatical. Too formal. Objects start to look like pronunciations of deeper rules. And once you think this way, the word particle becomes increasingly suspicious. Because if fields are primary and symmetries govern their behavior, what exactly is a particle? Supposed to be a little object? Or a stable mode of excitation we have mistaken for an object because it behaves object-like in certain conditions? That distinction may seem philosophical until you realize how much depends on it. If particles are patterns, then matter is less like a pile of beads and more like a repertoire of stable field events. And that moves us one step further away from the human picture of reality. The word particle is useful. That is why physics still uses it. Electrons hit detectors in localized ways. Photons transfer discrete amounts of energy. Tracks appear in chambers. Collisions produce countable outcomes. So particle language works. But usefulness is not the same as ultimate ontology. At deep levels, the mathematics treats what we call particles as quantized excitations of fields. They are not tiny classical marbles carrying self-evident identity through an empty box. They are manifestations of underlying field structure under certain conditions. This matters because the human mind desperately wants nouns. A particle sounds like a noun. A thing. A smallest object. A pattern sounds less secure. A pattern depends on structure. A pattern depends on context. A pattern can persist without being a little indivisible pellet. Yet much of modern physics points in exactly that direction. An electron is stable and repeatable. That does not necessarily mean it is best imagined as a tiny hard sphere. A photon behaves in ways that make little bullet of light a poor overall image. Quarks are never observed in isolation because of confinement. Collective excitations in condensed matter can act particle-like even though they are emergent. Quasiparticles, proving that particle-like behavior does not by itself establish elementary objecthood. This should force a conceptual upgrade. The universe may not be made of things in the primitive sense. It may be made of stable modes. Stable excitations. Stable correlations. Stable organizations of field behavior. Stable patterns permitted by symmetry and law. Matter, in this view, is not a pile of ultimate pebbles. It is a family of durable patterns that can be counted, scattered, and recombined. This is not demotion. Patterns can be real. In fact, much of reality may consist precisely in the stability of patterns. A whirlpool is a pattern in water. A wave is a pattern in a medium. A note is a pattern in vibration. A thought is a pattern in neural activity. A galaxy is a pattern in gravitating matter. Why should a particle not be a pattern in a field? And once you admit that, the entire emotional foundation of substance begins to shift. The world stops looking like matter made from little matter bits. It starts looking like stable organization all the way down. Now we must stay careful. This does not mean electrons are illusions. It does not mean particles are unreal. It means reality may not respect the metaphysical picture attached to our nouns. The electron is real. The question is what kind of real it is. And modern physics increasingly answers. Real as an excitation with invariant properties. Real as a repeatable pattern of field behavior. Real as a participant in law. Not necessarily real as a miniature classical object with a little hidden body. If that sounds cold, it is supposed to. Because this is one of the places where physics quietly takes away the furniture of common sense. Substance becomes structure. Thingness becomes stability. Identity becomes lawful recurrence. And once that happens, a larger question presses forward. If particles are patterns and fields are primary, where do the fields live? In space. But what if even that answer is provisional? What if the space we speak of is not the ultimate stage, but itself emergent from some deeper Order. This is where physics becomes most dangerous. Because so far we have only demoted objects, solidity, emptiness, and universal time. Now we are about to threaten the stage itself. For most of human history, space seemed untouchable as a concept. You could challenge the motions of objects. You could challenge the shape of Earth. You could challenge the age of the world. But space itself? Surely space is just there. Modern physics has already wounded that confidence through relativity by making spacetime dynamical. But some of the deepest frontier ideas go further. They suggest spacetime may not be fundamental at all. This is not established in the way relativity or quantum electrodynamics is established. It belongs to the frontier. But it is not fringe fantasy either. It is one of the central pressures emerging from attempts to reconcile gravity, quantum theory, black holes, and information. The basic intuition is this. If gravity, entropy, quantum entanglement, holography, and black hole thermodynamics are all telling related stories, perhaps space is not the base layer. Perhaps geometry itself emerges from something more primitive, information theoretic, algebraic, quantum relational, network-like, or otherwise pre-geometric. This is a family of ideas, not one settled doctrine. In the ADS/CFT correspondence, a gravitational spacetime in the bulk can be dual to a non-gravitational quantum field theory on a lower dimensional boundary. That is not proof reality. Is a hologram in the cheap popular sense. But it is an extraordinary case where spacetime description and non-spacetime boundary description are deeply equivalent. Then there are hints connecting entanglement entropy and geometry. Certain tensor network ideas. The suggestion that connectivity in space may be related to entanglement structure. The famous phrase, ER equals EPR, provocative and far from final, suggesting relations between wormhole-like geometry and entanglement. Again, careful. These are active areas. Not completed metaphysics. But the direction of pressure is unmistakable. Space may be less fundamental than relation. That sentence may be the hardest one in this documentary. Because if space is emergent, then the room we thought reality happened inside is itself downstream of something deeper. Distance becomes derivative. Nearness becomes constructed. Geometry becomes output, not input. Imagine what that does to human intuition. We use space to explain everything. Where something is. How far away it is. What touches what. What counts as local. What counts as inside or outside. If space is not fundamental, then these categories may be approximate features of a deeper order. That does not begin spatially. The world becomes not merely strange in behavior, but strange in framework. Reality is no longer things in a box. It may be a relational order from which the box appears. We do not yet know the final answer here. Loop quantum gravity, string theory, holographic duality, causal set approaches, amplitudes. Research, and other frameworks each gesture differently toward the nature of spacetime. No single universally accepted synthesis exists. But the very fact that leading physics is willing to consider emergent spacetime tells you how far the old picture has collapsed. The old picture said, space is obvious. Objects are inside it. Time passes. Laws act. The new pressure says, perhaps laws, information, quantum relations, and symmetry are deeper. And spacetime is a stable large-scale consequence. This is not a modest update. It is an ontological earthquake. And yet the earthquake remains incomplete. Because physics, for all its power, is not finished. There are things it knows with astonishing precision. There are things it strongly suspects. And there are things it still does not know. Honesty now matters more than drama. Because once reality becomes this strange, the temptation to overclaim becomes almost irresistible. So before we go further, we need to mark the frontier clearly. There is a bad habit in popular science. Whenever reality becomes difficult, people rush to certainty. They mistake conceptual momentum for proof. They treat elegant speculation as settled fact. They confuse promising direction with final answer. This documentary will not do that. Because one of the most important things physicists have discovered about reality is that the universe punishes premature confidence. Here is what we know with great confidence. Quantum mechanics works with extraordinary success. Special and general relativity work. Quantum field theory works in the domains where it has been tested. The Standard Model works astonishingly well. Entanglement is real. The vacuum is not classical emptiness. Time is not absolute. Information has physical consequences. Black holes and horizons force deep consistency questions. Here is what we do not yet know in final form. We do not have a complete empirically verified theory of quantum gravity. We do not know the ultimate nature of dark matter. We do not know the ultimate nature of dark energy. We do not know whether spacetime is fundamentally emergent or how exactly that emergence works if it is. We do not know which interpretation of quantum mechanics, if any, deserves ontological primacy. We do not know whether information paradox resolutions that look compelling in one framework generalize in the deepest sense. We do not know whether our universe is fundamentally finite or infinite. We do not know why the constants of nature take the values they do. We do not know why there is something rather than nothing in any final rigorous physical sense. That list matters. Because the terror and beauty of modern physics come not just from what it has clarified, but from how much it has clarified without completing the picture. We know enough to destroy the old reality. We do not yet know enough to fully rebuild the new one. That is where we live. Between demolished intuition and unfinished ontology. For some people, that sounds disappointing. It should not. This is what real progress looks like. It is not a tidy staircase. It is a landscape where some mountains have been climbed so decisively that they can never be unclimbed, while others remain in mist. And what has already been climbed is enough to change the entire emotional atmosphere of existence. You do not need a final quantum gravity theory to know that matter is not classically solid. You do not need a final TOE to know that time is not absolute. You do not need metaphysical closure to know that entanglement and information have transformed the picture. You do not need ultimate consensus to know that the object in empty space worldview has been deeply wounded. So the uncertainty is not paralysis. It is frontier. And frontier has a particular emotional quality. You can feel which direction the terrain is sloping even before the road is fully built. Physics is sloping away from primitive objecthood. Away from naive emptiness. Away from universal present time. Away from simplistic locality. Away from classical substance metaphysics. Whether the final landing place is, all is information, or, all is quantum geometry, or something far more alien than our current slogans, we do not know. But we do know the old village is behind us. And that raises another question that every sane person asks at this point. If reality is this strange underneath, why doesn't it look that way? Why do tables remain tables? Why do cats not visibly smear into superpositions in the kitchen? Why does the world feel classical if deep physics is not? That question matters because without answering it, the whole modern picture risks sounding detached from life. So now we need to understand the bridge. How the classical world appears. Why stable everyday reality exists at all. If quantum theory and relativity are so radically unlike everyday intuition, why did human beings evolve an intuition that works at all? Because the world we inhabit is not the deepest level of law. It is the macroscopic regime that emerges after averaging, decohering, stabilizing, thermalizing, and coarse graining have done their work. The everyday world is a success of compression. It is what reality looks like after enormous numbers of microscopic degrees of freedom have been organized into robust large-scale behavior. This is why classical approximations are so powerful. They are not arbitrary simplifications. They are the correct language for systems in which quantum details wash out or become inaccessible at ordinary scales. Consider a baseball. At the microscopic level, it is a seething hierarchy of particles, fields, charges, bonds, thermal agitation, and quantum rules. At the human level, it follows a trajectory. Both descriptions are real. One is deeper. One is usable for throwing. The same applies to solidity, temperature, pressure, fluid flow, chemistry, biological life, and most of engineering. The macroscopic world is not false because it is emergent. It is real as a higher-level stable pattern. That is crucial. A mistake often made in discussing deep physics is to say things like, "Nothing is really solid," in a tone that implies chairs are fictional. That is lazy. Better to say, solidity is real, but it is not fundamental in the way common sense imagines. Emergence is not illusion. It is layered reality. And decoherence helps explain why macroscopic systems do not usually display obvious quantum interference effects. Their phase relations become entangled with the environment so quickly and irreversibly in practice that classical predictability emerges for everyday observables. The environment continuously monitors certain features. The world becomes record-rich. Stable. Pointer states dominate. This is why your coffee cup does not behave like an isolated electron. Not because quantum law turns off, but because the conditions under which quantum superpositions display themselves cleanly at macroscopic scale are extraordinarily delicate. Reality classicalizes. Or, more precisely, our access to it becomes effectively classical in many domains. There is also thermodynamics. Huge numbers of degrees of freedom smooth out microscopic irregularity into statistical regularity. Temperature is not a property of one molecule. It is an emergent macroscopic description. So are pressure and entropy in their usual senses. The world of life depends on these layered stable regularities. No one could survive in a world that presented its deepest level nakedly at all times. The very possibility of memory, metabolism, chemistry, and biological stability depends on robust emergent behavior. In that sense, the classical world is not a lie the universe tells. It is the environment in which beings like us can exist. But there is an emotional cost. Because it means our experience was selected for usefulness, not for metaphysical transparency. We do not see the world as it is in itself at every depth. We see the world as a stable biological interface with the scales that mattered for surviving. Touch, color, object permanence, before and after, now and then, these are magnificent tools. They are not guaranteed to be final ontology. This should humble us. It should also deepen our wonder. Because the ordinary world, once understood properly, becomes more impressive, not less. A table is not demoted by being emergent. It is elevated. It becomes the endpoint of a chain of law running from quantum fields to chemistry to molecular structure to material rigidity to biological sensation. Emergence is not reduction's enemy. It is reduction's result. And yet a psychological shock remains. The world that feels obvious is not the ground floor. The world that feels obvious is the user interface. That is difficult to hear because human beings crave finality in what they can touch. We want the handhold to be fundamental. Physics says the handhold is real. But it is downstream. And that prepares us for the final emotional territory of this documentary. Not the science now. The psychology. What does it do to a human mind to learn that reality is not built for human intuition? What does it do to meaning, orientation, and even identity when the universe turns out not to be object-centered, present-centered, or human-centered at all? The scientific facts are difficult. The psychological consequences are often worse. Because human beings do not merely want truth. We want truth in a shape we can live inside. We want a world of objects, boundaries, places, causes, nows, insides and outsides, stable surfaces, distances that mean separation, emptiness that means absence, observation that means looking, time that means one shared river. That world is survivable. It is narratable. The modern physical world is survivable too. But it is much harder to narrate. And this may be the real reason so many people either resist physics or romanticize it badly. The truth it offers is not emotionally ergonomic. It does not present reality as a story arranged for human cognition. It presents reality as a layered lawful structure in which our most trusted categories are parochial. There is no universal now. No primitive solidity. No guaranteed separateness. No true emptiness in the classical sense. No final certainty that spacetime itself is fundamental. No promise that what feels obvious is deepest. That is not merely scientifically challenging. It is existentially abrasive. Because it means the human mind is not the measure of the real. The human mind is an adaptation to a narrow slice of it. We are not reality's preferred interpreters. We are local creatures who learn just enough of the interface to survive. And still, astonishingly, we built mathematics and experiment powerful enough to reach beyond the interface. That is one of the great dignities of science. Not that it confirms our instincts. That it lets us outgrow them. But outgrowing intuition has a cost. You lose the comforting fantasy that reality is basically what it feels like. You lose the easy picture of a world built from little objects in a neutral box. You lose the emotional security of believing that what is real must be what is imaginable. Physics strips that away. And then leaves you with something both colder and grander. A universe of lawful structure not scaled to the mind that discovered it. Some people hear that and think it diminishes humanity. I think the opposite. The fact that a species of evolved primates, tuned for fruit, weather, predators, and tribal life, could come to suspect the unreliability of its own intuition and build methods strong enough to expose it. That is one of the most extraordinary events in cosmic history. We learned not to trust our own default picture. That is intellectual courage in its purest form. Still, the wound remains. Because the new reality is harder to inhabit emotionally. If matter is pattern. If emptiness is active. If time is local. If observation is physical coupling. If separateness is incomplete. If information is law-like. If spacetime may emerge. Then what are we? We are not exceptions. We are instances. We are stabilized biological patterns inside the same lawful web. Our bodies are field-organized matter. Our memories are physical information. Our thoughts occur in time that is local, not absolute. Our existence depends on emergent classical stability rising from non-classical substrate. Our sense of self lives on top of a reality that is relational all the way down. That can sound bleak. It does not have to be. Because relational does not mean unreal. It means interdependent. Pattern does not mean fake. It means stable in a way deeper than substance metaphors capture. Emergent does not mean less important. It means achieved. You are not less real because you are not fundamental. Stars are not less real because nuclear physics underlies them. Music is not less real because it depends on vibrating matter. Meaning is not less real because brains implement it physically. The universe has not taken reality away. It has taken away a childish model of reality. And that is the difference between despair and maturity. But even maturity leaves us with one final haunting recognition. Physics has not made the world smaller. It has made it stranger than object language can easily contain. The universe no longer looks like a pile of things. It looks like a coherent but alien order in which things are stable appearances of deeper relations. And that brings us to the end. Not an ending in the sense of closure. An ending in the sense of synthesis. If everything we have followed is true, or even approximately true, then what kind of statement can we finally make about reality itself? Let us collect the fragments. Solid matter is not primitively solid. Empty space is not truly empty. Particles are not best imagined as tiny classical pellets. Fields are deeper than object language suggests. Time is not universal. Observation is not passive seeing. Entanglement complicates separateness. Information is physical. Black holes force reality to keep strict accounts. Symmetry governs what laws can be. Broken symmetry shapes what worlds can look like. Emergence explains why the classical world feels stable. And the possibility remains open that spacetime itself is not fundamental. If you say these separately, they sound like disconnected curiosities. If you say them together, a new picture appears. Reality may not be made primarily of objects. Reality may be made of structured relations that stabilize into object-like behavior. This is the shift. The world of common sense begins with things and adds interactions later. Modern physics increasingly begins with law, field, symmetry, state, information, and relation. And allows thingness to emerge afterward. A table is real. But its reality is the stability of many underlying relations. A particle is real. But perhaps as an excitation, a mode, a repeatable pattern, not a tiny bead. A vacuum is real. But as a physical state, not a metaphysical blank. A present moment is real for an observer. But not as the universal frame we once imagined. Even locality, that old comfort, survives in a subtler form than intuition wanted. Even space may turn out to be less stage than output. This does not make the universe ghostly. It makes it disciplined. One of the worst misunderstandings of modern physics is that deeper reality becomes dreamy, fuzzy, unreal. In fact, the opposite is true. It becomes harsher. It becomes less forgiving of primitive pictures. More mathematical. More constrained. Less interested in whether humans can emotionally metabolize it. The universe does not seem to be built from little furniture arranged in a room for our inspection. It seems to be built from lawful structure. And what we call objects may be the durable knots that structure ties in itself. That line deserves to remain. Objects may be the durable knots that structure ties in itself. Not illusions. Not fantasies. Not mere appearances. Knots. Stable enough to touch. Stable enough to build civilizations with. Stable enough to love, lose, name, and remember. But not necessarily fundamental in the old sense. This is why what physicists discovered changes everything. Not because it cancels reality. Because it relocates it. It moves reality away from surfaces and into relations. Away from appearance and into architecture. Away from things as primitives and toward patterns as achievements. And the haunting part is that this picture is probably still incomplete. We may yet discover that information is not deepest after all. Or that spacetime emerges in a way no current framework fully captures. Or that quantum foundations will be reinterpreted again. Or that a future theory will make our present language look as naive as Newtonian absolutes now. Look from inside relativity. But even if that happens, one lesson seems unlikely to be reversed. Human intuition is not the center of ontology. Reality does not owe us familiar categories. Physics has not made the universe safer. It has made the universe less centered on our habits of thought. That is the mature terror of science. It does not simply reveal that the cosmos is large. It reveals that the cosmos is under no obligation to resemble the mind that discovers it. And yet, somehow, the mind can reach it. That is the final wonder. A brief biological pattern on a small planet around an ordinary star inside one galaxy among hundreds of billions learned enough mathematics, enough humility, and enough experimental rigor to suspect that the world beneath experience is stranger than touch, stranger than sight, stranger. Then time is felt from inside the body. We may not know the final layer. But we know this. The old picture is gone. Reality is not merely a stage filled with solid props. It is a lawful negotiation of fields, geometry, information, symmetry, and relation. Matter is not just stuff. It is stable pattern. Emptiness is not absence. It is structured potential. Time is not one river. It is woven into spacetime differently for different paths. Observation is not just looking. It is physical involvement. The universe is not becoming unreal. It is becoming harder to reduce to nouns. And perhaps that is the deepest change of all. We came looking for the building blocks of the world. We may have found something stranger. That the world is less a pile of blocks than a way of holding together. That being is not merely occupation. It is organization. That what lasts is what law can stabilize. And that the most honest sentence modern physics can offer is not, reality is made of things. It is something closer to this. Reality is what remains coherent under the deepest rules we have found. That sentence is not comforting. It does not tell you what the universe is in the way a child wants to know. It does not give you a final object to hold. It does not restore the safe old world. But it may be the beginning of maturity. Because the point of physics was never to defend human instinct. It was to let reality correct it. And reality, so far, has corrected it mercilessly. The solid world became interactive. The empty world became active. The separate world became entangled. The fixed-time world became relativistic. The object world became field-like. The stage world became dynamical. And now, perhaps, even the dynamical stage may become emergent. The universe did not get smaller under analysis. It withdrew from familiarity. It became less like a thing and more like a structure. Less like a possession and more like a grammar. Less like a collection and more like a relation. And if there is any haunting comfort in that, it is this. We were never outside it. Our bodies. Our clocks. Our memories. Our instruments. Our theories. Our errors. Our questions. All of them were always part of the same reality whose strangeness we are only beginning to accept. So no, physicists did not discover one flashy secret that changes everything. What they discovered is worse. They discovered that reality itself may be nothing like the kind of thing human intuition thought it was. And once you understand that, everything changes quietly. The table. The vacuum. The clock. The star. The particle. The horizon. The self. Not because they disappear. Because they deepen. And in that deepening, the universe becomes at once more precise and more alien than the world we thought we were standing in.